This chapter will cover the idea of the derivative. Starting with section 2.1, we will cover limits and continuity. The goal of this video is to discuss the formal definition of a limit, evaluating limits using graphs, tables, and algebra. We'll discuss the definition of one-sided limits, and we'll also go over the definition of continuity. Let's look at the formal definition of a limit. The limit of a function describes the behavior of the function when the variable is near but does not equal a specified number, as seen in figure 1. If the values of f of x get closer and closer, as close as we want, to one number called L, as we take values of x very close but not equal to a number c, then the formal definition of a limit says the limit of f of x as x approaches c is L, and we write the limit as x approaches c, where the arrow means approaches or gets very close to, f of x equals L. So the idea here is we'll move closer and closer to c from the left and from the right along the graph, and those values will approach L. Notice that the function does not have to be defined to have a limit. Let's use the graph to determine the following limits. If we look at part A, this is read the limit as x approaches 1 of f of x. F of x is this blue graph right here given in the problem. So we're going to look to the left and to the right of 1 on the x-axis. So we're approaching x equals 1 from the left and the right, and we want to see what the function values are approaching. We notice that the function values are approaching L equals 1. So for part A, we would say the limit as x approaches 1 of f of x equals 1. Similarly, we'll still be looking at the same graph of f of x, but this time we'll be looking at the limit as x approaches 2 of f of x. So we're looking from the left and from the right. Notice that from the left, the limit is approaching 1, and from the right, the limit is approaching 2. Because these are not the same value, we would say the limit does not exist. We call does not exist D and E. In a future slide, we will discuss left-hand and right-hand limit notation. That's one-sided limits, so we can discuss what it looks like from the left and the right to give it a specific definition. Let's take a look at part C. We're looking at the limit as x approaches 3 of f of x. So coming from the left side of 3, we notice that the function is approaching 2, and coming from the right side of 3, the function is also approaching 2. Notice that the function is defined at 1, but the limits of the graph are approaching 2. So we would say the limit as x approaches 3 of f of x equals 2. Finally, for the limit as x approaches 4 of f of x, when we approach from the left and from the right, and the function is defined, the limit is 0. So the limit as x approaches 4 of f of x equals 0. Let's take a look at what it would be to evaluate a limit using a table of values. This says the limit as x approaches 2 of x squared plus 3x plus 3 over x minus 2. We're going to evaluate this using a table of values. You always want to use values on the left-hand side and the right-hand side of the limit value. So since we're doing x approaches 2, we want to go from the left-hand side and the right-hand side. So when we plug in 1.9 into our calculators, we're plugging into our function f of x. And f of x here is this function that's inside the limit. In our calculator, you'll want to start by pressing the y equals button. In y equals, we'll enter our function, making sure to use parentheses. So we have our function x squared plus 3x plus 3. We want to make sure to close the parentheses and divide by x minus 2 also in parentheses. You want to make sure that your table set has the ask option for your independent variable, so you'll press second window and change independent to ask, and you can leave dependent as auto. Then to access the table, you'll press second and graph. In the table option, you will then put in your function values. So starting with the left-hand limit, we plugged in 1.9, 1.999, and 1.9999. Then you can see that the function values are approaching negative infinity coming from the left-hand side of 2. You can start to plug in the values from the right-hand side, starting with 2.01. Then you'll plug in 2.0001, and then even closer with 5 zeros. Notice that the function values are approaching positive infinity from the right-hand side. So what we can see is that the left-hand side is approaching negative infinity, and the right-hand side is approaching positive infinity. Since the left-hand side and right-hand side are not equal, we would say that this limit does not exist. The left-hand side and right-hand side limits do need to be equal. We will discuss that in a future slide. Let's take a look at what it would be to solve a limit using algebra. This time we're looking at the limit as x approaches -7 of x plus 7 over x squared plus 9x plus 14. We'll start by using factoring, because if we try to evaluate at -7, it may be undefined. So let's start by factoring x squared plus 9x plus 14. So two numbers that multiply to be 14 and add to be 9 are 7 and 2. So we have x plus 7 times x plus 2. We see that the numerator and denominator factors are the same, so we can divide, leaving us with the limit as x approaches -7 of 1 over x plus 2. Now, if we were to take our -7 and plug it in for x, it will no longer be 0 in the denominator, as it would have been before. So once you evaluate the limit, you can then drop the limit notation and not before that. So notice that I've carried the limit notation in every step until this last step. I can drop it because I'll be plugging in the -7. So 1 over -7 plus 2 is -1 over 5. So the limit as x approaches -7 of x plus 7 over x squared plus 9x plus 14 is -1/5. Let's take a look at the definition of a one-sided limit, or left and right-hand limits, which we've briefly talked about. The left limit as x approaches c of f of x is L if the values of f of x get as close to L as we want when x is very close to and left of c. That is when x is less than c, and that notation is the limit as x approaches c from the left, that's what the minus sign is going to mean, of f of x equals L. The right limit, which is written x approaches c plus, that means x approaches c from the right, requires that x lie to the right of c or values larger than c. So the limit as x approaches c from the right of f of x is L. So if we go back to our previous problem where we had left and right hand limits, we can rewrite those values. So let's take a look at this previous problem where we found that the limits were left were negative and positive infinity. So we would say the limit as x approaches to from the left of f of x, I'm going to shorthand that function, is negative infinity, and the limit as x approaches to from the right of f of x is positive infinity. That would be your left and right hand notation for that problem. That leads us to the definition of continuity. A function f is continuous at x equals a if and only if the limit as x approaches a of f of x equals f of a. So there's a few things at play here. It says that the limit has to be defined. So the limit from the left-hand side and the right-hand side have to be the same, and both of them have to be the actual point when the function is evaluated at a. If you remember at the beginning of this video, we had that the limit existed even if the point was open. For continuity, the limit has to be the same from the left and from the right, and it has to be defined at that specific point. So it has to be a closed point. That means for a continuous function, we can find the limit by direct substitution, that's evaluating the function, if the function is continuous at a. So which functions are continuous? It turns out pretty much every function you've studied is continuous where it's defined. That's a polynomial, a radical, rational, which would be a fraction, exponential, and logarithmic functions are all continuous over their defined domains. Moreover, any combination of continuous functions are also continuous. So any addition or subtraction of those continuous functions is itself continuous over the defined domain. So there are two types of discontinuities that we'll see. One would be holes, or also known as a removable discontinuity, and the other would be a jump discontinuity. So another way you can think of continuity is once you put your pen down and you don't pick it up, that would be continuous. Wherever you have to pick up your pencil to continue the graph, that would be a discontinuity. So if we take a look at this graph, we're continuous at this point. We're defined left and right. We haven't picked up our pen yet. But then we get to this hole or removable continuity, and I have to pick up my pen to keep graphing. So our first discontinuity would be at x equals 1. And that would be a removable discontinuity or a hole. So if we continue going along our graph after x equals 1, I pass through 2 with no problem, but then I go up infinitely and have to pick up my pen to continue the graph at 3. That would be a jump discontinuity because I had to jump from one piece to the next to keep graphing. So we have a discontinuity at 3 and it's a jump discontinuity. So continuing along after x equals 3, we get to x equals 4. We have to jump again, and then we can continue. And there's two problems here. It's a jump and a removable discontinuity. So there's a discontinuity at x equals 4. The next video, we'll talk about the derivative.